Alright, let's discuss the Schur Zassenhaus theorem. So in the textbook this is called Schur's theorem. There's a lot of history behind the theorem. Schur originally proved a special case of it, and the Zassenhaus proved the generalization. And so here I'm stating the most general version, although we're only going to prove the first part. It says if H is a normal subgroup of G, and the greatest common divisor between H and its index is 1, then there exists another subgroup of G whose size is the index, whose order is the same as the index of H and G. Remember, this right here means that H is a Hall subgroup of G, and this says that H has a complement, namely K. Worth pointing out that this actually implies that G is isomorphic to the semidirect product of H and K. The second part is if you found another complement to H, all complements to H are actually conjugate to each other. So the reason we don't traditionally prove that part in this course is because the proof is very complicated and it actually relies on Thompson's theorem that groups of odd order are solvable. So we're only going to focus on this first part. If you have a normal Hall subgroup, then it has a complement. The proof, of course, will be by induction on the order of G. So one of the first cases we'll consider, so I'm modifying the proof from the textbook a little bit. They do a bunch of different cases, but some of the cases can be brought together, combined in this way. And so that's the approach I'm going to take, because I'm actually going to use this case to reduce ourselves to something very, very particular. And so the first case is that suppose that there is a subgroup of H that is a characteristic subgroup. So suppose there exists n characteristic in H. Well, remember H is normal in G by hypothesis, assumption. So we've proven that this implies that n is normal in G. And so now we're going to work with the quotient groups, G mod n and H mod n. And you can check that H mod n is in fact a Hall subgroup of G mod n. Why? Well, because n is a subgroup of H, and so it's not too hard to see here that this index of H mod n and G mod n is actually the index of H and G by one of the isomorphism theorems. And the order of H n has to divide the order of H. So you can see that there cannot be a common factor between H mod n and this index. So you have a normal Hall subgroup. So we can apply the induction hypothesis to G mod n and get a complement K. So it has size the index of H mod n and G mod n. And K is in this group. By the isomorphism theorems, there exists K prime subgroup of G, such that K prime mod n is equal to K. Well, the order of K prime then is the order of n times the index of H mod n and G mod n, which, as we've discussed, is equal to the index of H and G. Much the same way that H mod n divides the order of H, the order of n also divides the order of H, so these two also have no common factor. And why do I state that? Well, remember, n is normal, is characteristic in H, and actually n is normal in K prime by construction. And so we have a normal subgroup of K prime, and we've got this relatively prime condition. One thing that should be clear at this point is that the way this is constructed, we actually see then that the index of H and G is also the index of N and K prime. So we can do that replacement here. And thus we see N is a Hall subgroup of K prime. And so now we can apply induction to K prime. And so N has a complement in K prime. It has the right size. And voila, we have a subgroup of K prime, which is also a subgroup of G, whose size is the index of H and G. So we have a complement to H finally. And so we see we had to apply the induction hypothesis twice. And the main reason we had to apply it twice is because this group here almost had the right size. Its quotient had the right size, but it had this multiplication factor. So these extra steps were just to get rid of that factor. Another important step that we end up considering is the following one. Suppose there exists a prime dividing the order of H, and a CeLO P subgroup, such that the normalizer of P in G is not equal to G, so it's a proper subgroup. Well, then we're going to work with this normalizer. And this ratio right here, this index, you can check, divides the index of H and G. And clearly the index over this order over here divides the order of H, so these two are relatively prime numbers. And so we have this intersection here is a normal Hall subgroup of this normalizer. And so by the induction hypothesis applied to this normalizer, which is a proper subgroup, so we can apply the induction hypothesis, there is a complement, K, in this normalizer. Its size is this index of the intersection of H with the normalizer in the normalizer. Well, now we finally get to apply the Frattini argument, because H is a normal subgroup, and P is a CeLO subgroup of H. G is equal to this product. Now let's compute the order of G. Well, it's equal to the order of H times the order of the normalizer divided by the order of the intersection. Because we found this complementary subgroup, we can replace the order of this normalizer with this order of this intersection times the order of K. Because we're replacing this with this times that. And now we can cancel, and we have size of H times size of K. And so by this calculation, we see that the order of K is also complementary to the order of H. And so K is also complement for H. All right, so let's suppose that we're not in case 2. So in other words, for every CeLO P subgroup of H, the normalizer in G of P is G. Well, that means that when you intersect this normalizer with H, you get the normalizer in H of P. Well, you also get H. It's for every CeLO subgroup. Well, this means that P is a normal subgroup of H for all CeLO P subgroups. And that's one of the equivalent definitions for being nilpotent. So H is a nilpotent group. Well, remember, if you're nilpotent, you are isomorphic to a direct product of your CeLO subgroups. So let's write H as a direct product of its CeLO subgroups. Remember that, or it's not hard to prove that each CeLO subgroup is actually characteristic in H. In this particular case, because there's a unique subgroup of each, a unique CeLO subgroup of each size. And that's a property we had discussed when you discuss characteristic subgroups. If you have a unique subgroup of a given order, it has to be characteristic. So if T is at least 2, then there is a non-trivial characteristic subgroup, and we are back in case 1. So assume T is equal to 1. In other words, that H is a P group. So this part's not in the proof in the book. They actually work with the center first. But I'm doing it in a slightly different order. So I've reduced ourselves to the case that we're only working with P groups. Now I'm going to reduce to abelian P groups. So suppose that the center is a non-trivial subgroup, then we can apply case 1 again, because the center is a characteristic subgroup. So we can assume that the center is all of H. You can't assume that the center is trivial, because every P group has a non-trivial center. So if the center is all of H, then H is an abelian group. So we now have an abelian P group. Then the next trick to try is let P be the set of all pth powers of elements in H. If this group is not the trivial group, then you can prove that it is characteristic in H. How do you do that? Well, just remember that homomorphisms have this property, or isomorphisms have this property. So certainly any automorphism is going to send sigma x of P to sigma of x to the P, and you're going to see that it's going to send this set to itself. And so you can apply case 1 to this case. So we must be in the case that we have an abelian P group where this set is 1, which means that every element to the pth power must be the identity. This is what they call an elementary abelian P group. And elementary abelian P groups are just Cartesian products of the prime cyclic group. So unlike the book, I didn't reduce the theorem to the case where H was abelian. I've reduced it all the way to the case where H is a specific group. It's a kth power of a prime cyclic group. So in this one remaining case, the strategy is to show that there exists an injective homomorphism from G mod H into G. That would give you a group of the complementary order. And the strategy is to note that G acts on H by conjugation, and that this gives a rise to a homomorphism from G to the automorphism group of H, which is isomorphic to the general linear group. So in other words, we're working with matrices. And maybe one day I'll finish with the second part of this video. It is actually a very complicated construction, but there is a way to explicitly write down this homomorphism and construct this group explicitly. it's very complicated, and in some sense, all I would really be doing is doing the material from chapter 17 in disguise, but hiding all the abstraction and just writing down the most concrete stuff in this one special case. So it might be worth doing if there's enough students asking me to do it, but yeah,